Okay, just a couple announcements before we go ahead and get started. The last problem set will be handed out this week. It'll be due next Friday as usual. However, because your final exam is being handed out that Friday, I figured you probably don't want to be working on the problem set and the final exam at the same time. You could, I guess. It's fine with me. We'll have the final problem set due Friday at noon instead of at 5 p.m. That way you can just hand in the problem set and then pick up your final exam. And you won't have to do anything but quantum field theory that day, which will be good. The final exam is handed out on Friday at noon, as we decided on the December 5th, due the next day at noon. And let's see. Oh, yes, and there's an extra class this Friday at 10 a.m. Are there any other questions of an administrative nature? Did you guys do the problem set for today, by the way, more or less? Okay. It was not so bad, more or less? Okay, that's good to know. That's good to know. Okay, good. Yeah, if you need a little extra time on it, that's just fine. But I just didn't sort of want... I made it due today because we didn't have one due last week, and I thought that way we could space things out a little bit more. But if you do need an extra couple of days or something, that's just fine. Okay. How were the lectures last week? Could Guy live up to the impossibly high standards that I've set for this class? Okay. I'm sure not, but I'm sure he tried valiantly, for which we thank him. Okay, good. So today what I want to do is continue with the discussion of the quantization of fermions, the quantization of spinors, with the goal by, I suppose, next class of developing finally, I think what's the natural sort of conclusion of this course, the Feynman rules for quantum electrodynamics. Okay. And so far, so all we're going to be doing is putting together a lot of techniques that we've already sort of learned in this class, but there are a lot of little details that one has to keep in mind. There's a lot of indices, a lot of matrices to keep in mind. It's all nothing particularly more complicated than what we've already seen in this class. It's just that the calculations tend to get a little bit more complicated, and the notation tends to get a little bit more complicated. So for that reason, rather than directly diving into quantum electrodynamics, today what I'm going to do is introduce sort of a baby version of another baby version of quantum electrodynamics. We've already seen a couple baby versions, known as the Yukawa theory. This is the theory that describes the interactions between scalars and fermions. It's a very important theory. It appears in the standard model of particle physics. It appears, if we want to describe nuclear physics, it's the theory of pions. And so it's an important theory on its own right. And as we are understanding how to derive Feynman rules involving fermions, involving spinors, it's sort of an easy place to start before we get into the full complicated glory of quantum electrodynamics. Okay. So let me begin just by reminding you of a few things that you learned last week and the week before on the quantization of spin 1/2 particles. So, as usual in this class, we're going to be considering Dirac spinors, which are 4-component objects, typically denoted psi. The Lagrangian, as you know, is psi bar times the kinetic term I d slash minus m psi, where d slash is this fancy notation where it stands for d mu gamma mu, where the gamma mu are the Clifford matrices, which can be represented in our favored basis, such as the Weyl basis, in terms of 4x4 matrices involving the Pauli matrices. Okay. And psi bar is a fancy name for psi dagger times gamma 0, the first of the Clifford matrices. The classical equations of motion, obeyed by a Dirac spinor, are known as the Dirac equation. So I d slash minus m times psi is equal to 0, along with a similar conjugate equation for psi bar. And it's reasonably straightforward to figure out what the classical solutions to this are. We did this a little over a week ago, and you had some time on the homework getting familiar with these solutions. The plane wave solutions can be written in the following form. So psi is some constant spinner times e to the ipx. So that's what it means to be a plane wave. And as usual, there's one solution for each choice of 3 vector p, and then p0 is determined by solving the equation of motion, the Klein-Gordon equation, that sets p squared equals to m squared. And as usual, we're going to choose p0 to be greater than 0. That's the positive frequency solution. And similarly, there's a set of solutions typically written with a v instead of a u, where we choose the branch of solutions with p0 less than 0. Okay. And these u's and v's are 4-component spinners. They're just constants. So they can be written as column vectors. And in the Weyl basis, these can be written generally as follows. So there are 2 linearly independent solutions for u and 2 linearly independent solutions for v. You just find them by taking this plane wave and plugging it into the Dirac equation, and you get an equation for u that's something like p slash plus m times u is equal to 0. So that's just some matrix acting on a 4-component column vector, which you could then just go ahead and solve explicitly. And the solutions in the Weyl basis, there are 2 of them. And so they're usually labeled by an index s that runs from 1 up to 2. And as I believe you checked on the homework that's due today, you can simply write the solutions as follows. So for u, the basis of solutions for general p take the form that I've written here, where these zeta s's are just 2-component spinners. So zeta 1 is 1, 0, and zeta 2 is 0, 1. Or you could take any other basis for the zetas. You just have to choose 2 linearly independent 2-component spinners. And similarly, there are expressions for the v's. Okay? And there's just one small difference, which comes from the fact that we've chosen the opposite sign for p0 here, meaning leading to a minus sign right there. Okay. So is this something that's more or less familiar? I did ask you to prove this on a problem set, right? Okay, good. So for example, in class, we derived this in a particular frame, in the frame where the electron, where the spinner is at rest. And then one could derive this in a general frame, either by taking that result and boosting it, and remembering how spinners transform under a Lorentz boost. Or you could just go ahead and solve the full Dirac equation for general values of p. Okay, they'll both give you the same answer. Good. So this is a complete basis of solutions. And as with any other field that we study in this class, one can describe the Hilbert space of particles that arise when you quantize this field by taking the general field operator, so now regarded as an operator in a quantum mechanical theory, and expanding it in a complete basis of solutions, that is to say, expanding in Fourier modes. Okay. So that means we need to sum not just over the momenta, p, the 3 momentum p, that labels the momenta of the various Fourier modes, but also over this index s, that labels the two linearly independent solutions. And then the Fourier coefficients, so they'll be labeled by a momentum P and a sort of helicity label S. Those Fourier coefficients are then interpreted as raising and lowering operators that we use to construct the Hilbert space of the theory. Okay. So here I've written down an expression for psi, and there's a similar expression for psi bar. So psi bar, you just take the dagger and multiply it by a gamma 0. So that just means you get exactly the same expression, except that you have to do some bars and some daggering and some complex conjugating. Okay. And I realize that I'm using a slightly different notation. So here I wrote S as a subscript. Here I wrote S as a superscript and P as a subscript. But hopefully it's clear what I mean. And then we interpret the A's and the B's as operators that we can use to construct the full Hilbert space of the theory. And with one small exception, the construction of the Hilbert space of states of the theory proceeds exactly as it does with a scalar field. Okay. In particular, the A's and the B's so the A and B daggers are interpreted as operators that create an electron or positron, respectively, with helicity S and momentum P. Helicity now just being a fancy name for what we call that label S. Okay. As we described earlier, helicity, the way that I have chosen to write these spinors U and V are such that the helicity, I guess you would call it positive or negative, depending on whether the spin of the particle is in the direction of the momentum of the particle or transverse to the direction of the particle. One could always choose another a different basis of spinor, a different basis of spinors that are not a helicity basis, but the helicity basis is the one that's conventionally used. So you should think of these helicities as analogous to the polarizations of a photon. So just like we conventionally describe a photon, say, described by two polarizations transverse to the direction of propagation of the photon, you describe an electron in terms of the two helicity states with either positive helicity or negative helicity. Okay. So just just as you traditionally maybe think of a spin 1/2 particle as having spin up or spin down in the z direction, you could also think of a different basis where you think of spin in the plus x or minus x direction. So you could always go to different bases of states to describe these, these plane wave solutions. And at the end of the day, unless you particularly care about the, the state of an incoming electron, that may or may not matter. So typically, if you're studying some scattering process and you're not measuring the helicity of the electron going in or the electron going out, then you'll end up summing over these helicity indices S in the same way that in the problems that you did the week before last, when you studied unpolarized photons, you ended up summing over the polarizations of the photon, getting some sort of simplifications there. Okay. So for most of the time, this index S is just something that's going to float along, and you should just think of it as labeling the two different possible states of an electron in the same way that you have two different polarizations of a photon. Okay, and similarly, the A's and the B's are operators that remove an electron or a positron with an appropriate amount of momentum and helicity. Okay. The ground state of the theory, the vacuum state of the free theory, that is to say the non-interacting theory, is defined by the condition that it is annihilated by all of these lowering operators. And the states that contain electrons are then found by acting on this vacuum state with these creation operators A dagger and B dagger. However, there's one crucial, incredibly important distinction between this theory and the scalar field theory that we were studying earlier in this class. And this distinction was, I guess, the essential topic of Guy's 2 lectures last week, which is that the A's and B's are anti-commuting rather than commuting variables. That means, so that reflects the fact that the particles that are created here have are fermions rather than bosons. Okay. The electron and positron states are fermions. The wave function describing 2 electrons picks up a minus sign when you interchange the 2 electrons. Now, there are a variety of ways of seeing that when you quantize spin 1/2 particles, they need to have fermionic statistics rather than bosonic statistics. So I guess I don't actually know which arguments Guy gave to you last week. He said he was very convincing, but he didn't tell me which arguments he gave. So one of the arguments that you can give is that if you try and go through this construction and you assumed that the A's and B's obey commutation relations rather than anti-commutation relations, and then you wrote down the Hamiltonian of the theory, you would find that the Hamiltonian is unbounded below. Okay, so that the theory would be unstable. There's infinite negative energy. Okay, so that's a pretty good argument. You can also show that you would have trouble with Lorentz invariance. That's actually something that we'll encounter in a slightly different context a little later on in this lecture. I don't know, which argument did he give? He did the first one. Okay, so that's good, because later on in this lecture I'll touch a little bit on the problems with Lorentz invariance. Okay, and it's a general fact, one that is sort of beyond the scope of what we'll study in this class, at least this semester, so it turns out to be a general fact that particles with odd spin, that is to say, with half-integer spin, must have bosonic statistics, that is to say, when you take the wave function of 2 particles with, Jesus Christ, okay, fermionic statistics, okay. You know, next year, if they ask me to teach this class earlier in the day, I may not make so many stupid mistakes. I'll have to make much more subtle and interesting mistakes. Particles with half-integer spin must have fermionic statistics. If you take a 2-particle state, the 2-particle wave function, and you interchange the 2 particles, you'll get a minus sign. Whereas particles with even spin, that is to say, scalars, spin 1 particles such as photons, spin 2 particles such as gravitons, and so forth, must have bosonic statistics. So the relationship between the spin, that is to say, the transformation properties under Lorentz transformations, and the statistics, that is to say, the behavior of the wave function when you interchange particles is not at all obvious. It's not supposed to be obvious. So you encountered it as a fact, as just sort of something that happened to be true for this particular Lagrangian describing spin 1/2 particles last class. But you might imagine that there are some other sort of dynamics describing spin 1/2 particles that could allow them to be bosons. But it turns out that when you're studying quantum field theory in 4 dimensions, that's just not the case. Okay? And this is a kind of deep and one of the most important results in quantum field theory known as the spin statistics theorem. Okay? Just as an aside, the spin statistics theorem is not true if you're studying quantum field theory in lower dimensions. Okay? So in particular, if you study, for example, materials physics, so let's say you study a 3-dimensional material or a 2-dimensional material. So for example, if you study the fractional quantum Hall effect, which is the description of electrons that are bound to some 2-dimensional surface, so that would be described by a theory in 2 + 1 dimensions, 2 space, 1 time, instead of 3 + 1 dimensions. There is no spin statistics theorem in 1 less dimension. And it's possible for particles to have other sorts of, or rather, I shouldn't say there is no spin statistics theorem in 1 less dimension. There are different spin statistics results in 1 less dimension. And so, in fact, the kinds of statistics that particles can have in 1 less dimension is much richer. There are particles that are neither fermions nor bosons in 1 less dimension. They're called anyons. It is unclear experimentally whether they have actually been observed in fractional quantum Hall systems. I think it's still a subject of some controversy. But it's really a very exciting area of open research. Okay, constructing particles that are neither fermions nor bosons but have some more complicated statistics. And in 1 + 1 dimensions, if you study, say, I guess what you call it, a quantum wire or something like that, the possibilities are even more wild. Okay, the distinctions between integer spin and half integer spin, even spin and odd spin, kind of break down in lower dimensions. Okay? So that's something that's very interesting. Yes, there's a question. In a higher dimension, so the slogan that you should keep in mind is that all of the properties that we're discussing here follow from Lorentz invariance. Lorentz invariance, like rotational invariance, gets more and more powerful in higher dimensions. So think about the example of rotational invariance. If you're just considering if you're in flatland and you consider rotations, you just have a 1-dimensional rotation group, okay, just one angular momentum. Whereas in our world, you have 3 rotations, okay, and 3 is bigger than 1. So the rotation group is more constraining in higher dimensions. Similarly, the Lorentz group is more constraining in higher dimensions. Okay, so the spin statistics theorem is, constraints get more and more stringent as you go higher and higher dimension. In lower dimensions, more and more wild possibilities are available that are not available in higher dimensions. Anyons is the classic example. These are these particles that have statistics that's neither bosonic nor fermionic. So in particular, one of the really interesting things that's cool is that, you might think, so a boson is, okay, I'm never going to get anywhere. Okay, I'll talk there in 2 minutes. So a boson is a particle such that if you take 2 identical particles and you interchange them, the wave function has a plus sign. And a fermion is one where you pick up a minus sign. So you might think that the most general thing you could do would be to get a phase, okay? And indeed, those are the most natural thing you could do. You could get things that pick up an arbitrary phase that's neither just plus or minus 1 when you interchange the 2 particles. But there are also particles, conjectured particles that appear in the quantum Hall system, conjecturally, that have non-abelian statistics, okay? Which means that the wave function lives in some group and you have to multiply by some non-trivial matrix, okay, when you interchange particles. And so when people think about ways of constructing quantum computers, for example, what they want to do is braid these different particles around one another in complicated ways and use this to, use this to sort of encode correlations in the topological properties of this braiding stuff. Okay, it's all pretty interesting. It has nothing to do with what I was planning on talking about today. Are there any other questions? Yes. Okay, good. Okay, so but hopefully you learned last class that the A's and B's are anti-commuting variables. So, for example, the A's anti-commute with one another, as do the A daggers, as well as the B's. And the only non-zero anti-commutation relations are those between an A and an A dagger and a B and a B dagger. So first of all, the anti-commutator between an A and an A dagger, there's a delta function that says S equals to S prime. Okay. That just says that the S labels two different species of particle, two different types of particle, the different helicity states. There's some stupid normalization factor. And then there's a delta function that sets P equals to Q. And likewise for the B's. Okay. So in particular, what this means is that when we build up the space of states, the Fock space, that is to say the space of states, built out of these raising and lowering operators, includes things where you have, say, a bunch of A's acting on the vacuum and a bunch of B's acting on the vacuum. So let's say the A's all have momenta P1 up to Pn, and the B's all have momenta Q1 up to Qm. But the important point is that all of the Pi must be distinct. Or rather, I should say, all of the pairs Pi-Si must be distinct. Because as usual for fermions, you can't have two particles occupying the same state. That's the Pauli exclusion principle. Okay. So the Fock space for fermions is much simpler than the Fock space for bosons. For bosons, you could take a raising operator and take it to the nth power to get an n particle state, n particles with a given momentum. For fermions, you only have 0 particle and 1 particle states. Okay. So we now have a Hilbert space, the fermionic Fock space, and we have the operators that we're interested in, these field operators. We now want to go ahead and start computing things. So we want to go ahead and compute correlation functions. So we wish to compute the observables of the theory, namely the correlation functions. Which will take the form of the expectation value of a bunch of fermions in the vacuum state. So here, for example, I've written down the 2-point function of 2 of these Dirac spinors. And can anyone tell me what this 2-point function is? Have we been paying attention? Let me give you a hint. Okay, so the Dirac particle, the Dirac theory describes a particle with charge. So there is a global charge rotation symmetry, under which, psi transformed like this, and psi bar transformed like this. Okay. This is how we coupled the theory to a gauge field. What was the answer? Yes. So this, of course, is equal to 0 by charge conservation, for the same reason that when we were studying a scalar field, a complex scalar field, say 2 phi stars, so that would be equal to 0. Okay. So for example, psi is the operator that either creates an electron or destroys a positron, but no matter what it does, it increases the amount of charge by 1. So if you take the vacuum state, you act with 2 psis. No matter what you've done, you've either created electrons or destroyed positrons, but you've increased the amount of charge by 2. So its overlap with the vacuum state has to be 0. So this correlation function has to vanish. Okay. Good. Okay, so that one was easy. The non-zero correlation functions are all going to take the form something like, say, 1 psi and 1 psi bar. Okay. So here I've taken the point at which I've inserted the psi bar and set that to be at the origin, x equals to 0. Of course, by translation invariance, I could take it to be whatever I want. So I've just set it equal to 0 for convenience. And then this object is something that we can compute fairly easily in free field theory. So when we studied the scalar field and we wanted to compute these correlation functions, we came up with 3 different ways to compute them. So one way to compute this would be just to take the expression, the expansion for psi in terms of raising and lowering operators, insert this into the expression, just expand out in terms of raising and lowering operators, use the harmonic oscillator algebra, and you would get some answer. Okay. That's one way of doing the calculation. Another way of doing the calculation would be to use the fact that this 2-point function is a Green's function. That means that it has to be a solution to the wave equation with a delta function source. Okay. In this case, the wave equation is the Dirac equation. So that means that this would have to be a solution to the Dirac equation. Okay. So that would be another way of solving for this. And the third way of doing it would be to use the Feynman path integral. As you learned last week, when you formulate the Feynman path integral for fermionic particles, it's a little bit subtle as compared to for bosonic particles, because when you think about the classical Dirac field, you have to think about it as an anti-commuting variable rather than a commuting variable. And so you have to do what are known as Grassmann integrals, anti-commuting integrals, instead of commuting integrals. So this is something that hopefully you got at least a little familiar with last week, okay, more or less. Were you all, I mean, you spent about a lecture on this, I understand. Okay. So what I thought we could do, because those Grassmann integrals are still probably rather unfamiliar to you, I thought I would first derive this just in the completely boneheaded way by using raising and lowering operators, and then I would derive it again using the fermionic path integral, using Grassmann variables, because that would at least give you at least a little bit of chance to kind of get familiar with that. And then we'll go ahead and use this fermionic path integral approach to understand the derivation of the Feynman rules in the theory. Okay. So that's what I was planning on doing today. Maybe before I do so, this has all so far mostly been review. Let me pause and see if there are any questions before we actually dive into the computation. Any questions? So I understand that the whole notion of anti-commuting classical variables, Grassmann variables, is pretty confusing. Don't worry, you'll have plenty of chance to practice on your next problem set. Okay, good. So please let me know if there are any questions. Okay. So let's just go ahead and compute this directly by inserting this sort of master equation here for the expansion of psi in terms of raising and lowering operators. So before I do so, let me just make one important point about exactly what it is we're computing here. So psi is a 4-component object. You can think of it as a column vector. And psi bar is another 4-component object, which you could think of as a row vector, if you like. When I write down expressions like this, I'm really computing a 4x4 matrix. Okay, so there's really secretly an index on psi and another index on psi bar. So I'm computing a 4x4 matrix. Usually, what I'm going to do, if I can help it, is suppress that index. But we have to keep in mind that we're computing a 4x4 matrix here. Okay, so this is some sort of 4x4 matrix. In the present case, because it's a psi times a psi bar, that's completely unambiguous, and so there's no possible way that you could get confused. I could have also written something like, psi bar of x, psi of 0. Okay, that's something that we'll compute later on in this lecture. That is something that's a little ambiguous, because then here I have a row vector times a column vector rather than a column vector times a row vector. Okay, so you could interpret that expression in 2 ways. You could either keep these indices free and view this as a 4x4 matrix, or you could contract those 2 indices together. Okay, so if I don't tell you what's going on, the notation is a little ambiguous. So let me tell you what's going on. What I'm going to do is compute the 4x4 matrix. Okay, I'm not going to contract those indices together. Okay. Of course, we could contract those indices together. It would be easy to do. You just contract the alpha and the beta index. But let's go ahead and compute this 4x4 matrix. Okay. So I need to plug in this expansion of psi in terms of the raising and lowering operators. So the first thing is that you have a sum over the helicity states and the momenta for both psi and psi bar. Okay, there was that normalization factor, the square root of 2 omega p and 2 omega q. P and S are the expansion of psi, and Q and S prime are the expansion of psi bar. There's some factors of 2 pi cubed that I'm just going to okay. Let's just, let's keep life simple and forget about the factors of 2 pi cubed for now. I have a PhD, so I'm allowed to drop factors of 2 pi when I feel like it. It's one of the secret privileges. Okay, and then we get this expression that we wrote down earlier. Oops. So there's this guy, which comes so that's the one that comes when we expand psi, and then we have the one that comes when we expand psi bar, so that has a dagger, and all of the various U's and V's are going to be barred as well. Okay. Oh, and those S's are all primes. Okay. So now what we want to do is we want to use the fact that the vacuum state is defined to be annihilated by the A's and B's when you act on it from the left, and the vacuum state's annihilated by the A daggers and B daggers when you act on it from the right. Okay. That's just the Hermitian conjugate of the statement that A and B annihilate the Ket vacuum, so A dagger and B dagger annihilate the Bra vacuum. So the only term that's going to be non-zero when you use that is the term that has an A on the left and a B on the right. Okay. So it's A, P, S, A, Q, S prime dagger. And then you have this combination of U's and U bars. We now can use the fact that these guys will anti-commute unless P is equal to Q. So if P is not equal to Q, then you just anti-commute them through one another. You pick up a minus sign. But more importantly, you get an A acting on the vacuum, which is equal to 0. Okay. So the only non-zero term is one with a delta function that sets P equals to Q and S equals to S prime. Okay, so that comes from this commutation relation here. So we can use that to do, say, the Q integral. And what we're left with is an integral d3p over 2 omega p. So S prime has been set equal to S, and Q has been set equals to P. And so we get this spinor stuff, so a UPS, U bar P S, all times e to the IPX. Oh, I'm sorry, I forgot my e to the IPXs here. Okay. So there was an e to the IPX here. So e to the IPX and an e to the minus IPX. Sorry about that. Okay. That was just from the expansion in terms of the raising and lowering operators. There are none of them appearing over here because that guy was expanded at the origin. Okay. So e to the I qx would be equal to 0. Okay. So you get an e to the IPX. Okay. Okay. Now, on the problem set that was due today, you actually worked out precisely what this sum was. Okay. So this is the integral d3p over 2 omega p times, so it's a 4x4 matrix, okay, which is very simple. It's just p slash plus m times e to the IPX. You guys did that on the problem set due today? I think I asked you to do that, right? Okay. And that's, so I'm just using here the fact that when you sum over these helicity eigenstates, over these U's and P's, these helicity states, you just get this very simple 4x4 matrix, p slash plus m. You should think of this as very similar to the polarization sums that you did when we studied the scattering of unpolarized light in scalar QED. So in that case, when you summed over the product of two polarizations, an epsilon mu, epsilon nu, when you summed over the polarizations, you got a g mu nu. So similarly here, when you sum over the helicity states of an electron, you get a very simple answer. Oh, I'm sorry. Probably. Q's, Q's. Everything's a Q. Yes, Q, Q, Q. Any other mistakes? Okay. No other mistakes? Good. Okay. So if you wanted to, you could actually rewrite this a little bit using the fact that every time you take a d by dx on this e to the IPX, you bring down a factor of IP. You could write this as minus I d slash, so d by dx mu times gamma mu, plus m times the integral d3p over 2 omega p e to the IPX. Okay. So the reason why this is an interesting thing to do, why this is a useful thing to do, is in fact that this quantity here is something that we've encountered before. Can anyone tell me what it is? It's the Feynman propagator. It's the propagator of a free scalar field. In fact, it's not exactly the Feynman propagator because I didn't have a time ordering symbol here. It's just the 2-point function. So what we see is that a very easy way of constructing spinor propagators is just to take derivatives of scalar propagators. So here I computed the expectation value of psi bar. So similarly, we can compute the expectation value of psi bar psi. So here, this is a nearly identical computation. And you get the exact same thing, except with a minus sign. So one way that you can think of that minus sign arising is because, so this was the expectation value of psi times psi bar. And to go from psi bar to psi, you need to anti-commute these two guys, the psi and the psi bar, and when you anti-commute, you pick up a minus sign. Again, let me remind you that when I write down this expression psi bar psi here, I'm thinking about this as a 4x4 matrix. Okay, I'm not contracting those two indices, which is why I have a d slash over here. The gamma mate d slash d by d mu, d by dx mu, gamma mu is a 4x4 matrix. It's a Clifford algebra matrix. Is there a question? Yes. Yeah, it's yes. I mean, it is. Let's put it this way. This really arises because the Dirac equation is the square root of the Klein-Gordon equation. Okay, the Dirac equation and the Klein-Gordon equation are intimately related, and so you shouldn't be surprised that the Green's functions, the two-point functions for these two equations, are intimately related. The gauge field, it's a little more complicated. The gauge field is a little more complicated. That's right. Good question. Other questions? Good. Okay. So when we compute scattering processes, remember that we're not necessarily interested in the correlation functions per se, but rather in the time-ordered correlation functions. Okay. So we get scattering amplitudes from time-ordered correlation functions. So expressions where we take the expectation value of things like the time-ordered product of psi of x with, say, psi bar, okay, of y. So there's one important subtlety that arises when we take time-ordered products of fermions as opposed to bosons. So remember the time-ordered product. So let me give these fields different names just so that the notation is a little bit more clear. So let's imagine that we have two fermions, psi and chi. Then the way that we define the time-ordered product, so if these were just bosons, I would define the time-ordered product as follows. Okay, thinking about these as quantum operators, the order in which I take them matters, and the way that I define the time-ordered product is, well, if x happens before y, then we put psi first, and if y happens before x, then we put chi first. Okay. So that's the definition of the time-ordered product of these fields if they're bosonic. But you see that effectively what we've done here is reorder the fields chi and psi, and if they're fermions, the natural thing to do is not commute the fields together, but rather to anti-commute them. which will lead to a minus sign. Okay. So a priori, for fermions, you could really imagine defining the time-ordered product in either way. Okay. You could either define it with a plus sign or a minus sign there. Okay. And so you should really think of this minus sign as part of the definition of time, what we mean by time ordering for fermions. So this is going to happen again and again as we think about fermions. There are going to be funny minus signs that crop up all over the place. Okay. So what I'd like to do now is I'd like to just take that minus sign as part of what I mean as the definition of time ordering for fermionic particles. And we'll go ahead and compute this. Okay. Compute the expectation value of this time-ordered product. And then look at it. And then what we'll actually see is that if we took the other sign, you would get an answer that's not Lorentz invariant. Okay. So it turns out that this sign is necessary for Lorentz invariance. Okay. And indeed, this is really part of what I was referring to earlier when I said that if you try and interpret spin 1/2 particles as bosonic instead of fermionic, then you get in trouble with Lorentz invariance, with causality, not just with the unboundedness of the energy. Okay. And in general, when we take the time-ordered product of a bunch of fields, say psi 1 up to psi n, then you'll get you need to think about all possible orderings of the times x1 up to xn at which you have these fields, and then every time you interchange two of the fermions, you pick up a minus sign. So minus, say, psi 1 up to psi n minus 2, psi n, psi n minus 1, all times some appropriate theta functions here, plus dot, dot, dot. Okay. So in general, you take a minus sign whenever you interchange two fermions. By the way, this minus sign here, you could take it as part of a definition, just as a definition of what we mean by time ordering. But if you think about these psi's and chi's as Grassmann variables that classically anti-commute, then it just follows from the fact that the time ordering of psi of x, chi of y should be equal to minus the time ordering of chi of y, psi of x. So really, this minus sign here is just part and parcel of what you need when you have anti-commuting fields rather than commuting fields. Yes? Yeah. Well, I would say that breaking of Lorentz invariant, well, let's see. Okay, breaking of Lorentz invariance usually leads to problems with causality. Okay, and indeed, so maybe I wasn't speaking terribly precisely, but yeah, okay. What I meant to say is that you end up with, so as we'll see in just a minute, you end up with something, or maybe I'm not going to show it. Yeah, okay, it's not so hard to see. But you'll end up with something that's not Lorentz invariant, and I believe you could use that to go kill your grandmother, right? I mean, I believe that you could use that, yeah. Right. Sorry, was that a little too outre? Okay, good. Okay, well, let's go ahead and compute this guy. Okay. So let's compute now the Feynman propagator, that is to say, the time-ordered expectation value of psi times psi bar. Okay. So this is now the sum of two terms. Okay. So the first term, so I'm just using here the definition of t. So the first term is the expectation value of psi times psi bar, which is so minus I d slash plus m times this Feynman propagator, the integral d3p over 2 omega p e to the ipx. And then you have to multiply that times a theta function, x0 minus y0. So you get a psi bar if x happens before y. And then we have to add to that the corresponding term where x happens after y. Or rather, you have to subtract from it because of this minus sign here. The corresponding term if x happens after y. Okay. So then you can just use then the fact that this expression here. Okay, and I forgot a minus sign, of course. So there's this minus sign here, which cancels this minus sign coming from there, so you get a plus. The exact same thing. Okay, the integral d3p over 2 omega p e to the I. Now it's a minus ipx. Sorry, I guess x minus y. So it was e to the minus ip x minus y times a theta of y0 minus x0. Okay. And of course, this expression here is precisely the Feynman propagator. Okay. So this is the Feynman propagator for a scalar. So that means that you can write this as minus I d slash plus m times the Feynman propagator, which, as usual, is a little bit more nicely written in momentum space. Okay. I'll put the factors of 2 pi back in because, well, that factor of 2 omega p disappears when we go to a d4p instead of a d3p. So you get an I over p squared minus m squared with the usual I epsilon factor times e to the ipx. And I guess that's an x minus y. Or, if you wanted to write this, and this is the form that we'll end up using most of the time, you get an integral d4x, 2 pi to the 4th, times I p slash plus m, just taking the derivative explicitly, over p squared minus m squared plus I epsilon, times e to the I px minus y. So what does this mean? This means that when we study spinors, the spinor propagator in momentum space is going to be p slash plus m over p squared minus m squared. Okay. So we should compare that to the scalar propagator, which was just 1 over p squared minus m squared. Okay. So again, this is really all coming back to the fact that the Dirac equation is the square root of the Klein-Gordon equation. The Dirac equation is the square root of the Klein-Gordon equation. So the Green's function for the Dirac equation is the square root of the Green's function for the Klein-Gordon equation. And that's basically what we're seeing here. Okay. Now it has to be the square root in the sense of 4x4 matrices. Okay, so we've got these funny p slashes floating around, but that's basically what's going on. There's a question. That's correct. Yeah. Yes, and it's for exactly the same reasons. That's a great point. So, if you go through this derivation here, the basic point is that when you computed this guy, you ended up with this sum over polarizations here. Okay. And that gave you the P slash plus M. Okay. And so you're exactly right. So if we went through and did the exact same computation for the photons, I don't actually remember if this is how I did the photon. I don't remember how I derived the photon propagator. I think I used the path integral point of view. But if we did it in this sort of more straightforward raising and lowering operator point of view, you would have gotten the sum over epsilon star times epsilon, which would be that G mu nu, okay? Which would be precisely the propagator of the photon in Feynman gauge. Okay, great. Good point. That's exactly correct. Good. Other questions? Okay. One of the important points to notice about this is that this propagator is linear in 1 over p rather than quadratic in 1 over p. That comes from the fact that the Dirac equation is a first-order equation instead of a second-order equation. Now, if you wanted to, you could go ahead and repeat this exercise, but but changing that sign there. And if you did that, you would find, so that's what would happen if we tried to interpret these particles as bosons instead of fermions. And you would find that this propagator is not Lorentz invariant. Okay. And that, of course, would lead to problems with all sorts of problems with, causality and grandmothers and so forth. Okay. So that's why that's another way of seeing why these spin 1/2 particles need to be fermions. Questions? Okay. So, as usual, we could also derive this using a path integral point of view. And, yes, question. Sure. Yes. That's correct. Yes, but in this case it would be the anti-commutator would be the relevant quantity to compute. That's correct, yes. So as with the scalar field, the thing that has to vanish outside the light cone is the commutator. With a fermionic field, the thing that has to vanish outside of the light cone is the anti-commutator. Now, if you took more complicated observables, things that are not linear in the fields, but say are quadratic in the size, so something 2 fermions is a boson, okay? So if you computed, for example, the correlation function of a bunch of these guys, say spinor bilinears outside of the light cone, those are bosons, and there would be the commutator that would need to vanish. What's that? Sorry. Uh-huh. Well, let's put it this way. Scalar observables, that any scalar observable you could compute would be a bilinear, and that would be a bosonic operator, and then you would compute the commutator. Maybe I'm not quite seeing what your question is. Okay. Okay. Well, feel free to ask. Yeah. Okay. Good. Okay. Yeah. So, just because all of this business with Grassmann variables and path integrals and all that stuff is going to be kind of new, what I would like to do is now present another derivation of this from the path integral point of view. Okay. And this would be this will also be a warm-up to our study of Feynman diagrams and our derivations of Feynman rules from the path integral point of view. Now, path integrals with fermions are just like path integrals with bosons, except that there's some funny minus signs. Okay, so from a practical point of view, all you ever need to do is understand what the algorithm is for working out those minus signs, and you'll be fine. But I want to try and do it a little bit more systematically this class and next class, just so that you understand exactly how everything works. Okay. So let's first just consider a free Dirac fermion. And as in the case of a scalar field, if we want to compute correlation functions from a path integral point of view, then you need to introduce some sources that couple to the fields of your theory. Okay. So typically, so here, psi and psi bar. So psi is the field of the theory. Just as phi and phi bar for a complex scalar field can be viewed as independent degrees of freedom, psi and psi bar can be viewed as independent. And so we can integrate over them separately. And I've introduced here sources, eta and eta bar, which couple to psi and psi bar, so that when we take derivatives with respect to eta and eta bar, you'll pull down factors of psi and psi bar, and that will allow you to do things like compute correlation functions. Okay. So here, eta and eta bar are sources. So eta is the source for psi bar, and eta bar is the source for psi. So eta and eta bar are anti-commuting. They need to be anti-commuting because the total Lagrangian should be commuting. It should be a boson. It should be a real number. And so they have to be anti-commuting because you multiply them by a psi, something anti-commuting. The product of two things that are Grassmann is commuting. And likewise, they need to be spinors. They need to be four-component spinors so that the action is a scalar, okay, by Lorentz invariance. And we can then compute correlation functions in the theory by evaluating this path integral and taking derivatives with respect to eta and eta bar. The subtlety is that since eta and eta bar are Grassmann variables, their derivatives are Grassmann as well. If x is a commuting variable, then so is d by dx. So if eta is a non-commuting variable, an anti-commuting variable, so is d by d eta. Okay. So the variational derivative with respect to eta of x is an anti-commuting rather than a commuting derivative. Okay. So mixed partial derivatives are not equal of Grassmann variables. Mixed partial derivatives have a minus sign. Okay. Yes? Okay. They are not continuous variables. They're Grassmann variables. Okay. You know, exactly, if you like, you could view this all as some set of formal symbols. Okay, I'm introducing some sort of symbols, eta and eta bar, that I'm calling Grassmann variables, psi and psi bar that I'm calling Grassmann variables. The action here, is a real number. It's a function, but it's a function that doesn't depend on commuting variables, on anti-commuting variables. So what I mean when I minimize that function, I have to define what I mean. Okay? And when I define, and the way that I define what I mean is I define what I mean by derivatives. Okay? Right? So, the action is a real number. Okay, so you could imagine looking at its minimum, but you need to minimize it over some domain. The domain over which you're minimizing it, it's not like a real number, like the value of a scalar field, but it's a Grassmann number. Okay. Now you don't know what that means until I tell you what it means. I tell you what it means by defining what a Grassmann derivative is. I define what a Grassmann derivative is so that it's minimized on the equations of motion. Okay. So if you like, this is just some formal symbology that we're introducing so that you can manipulate it's a formal set of rules we introduce so that we can manipulate path integrals for fermions just like we do for bosons. Okay. And if you like, all this is this is a very complicated set of rules that we're introducing that allow us to keep track of minus signs. Okay. That's all it's doing. It's just some as we saw, you can derive Feynman diagrams, Feynman rules, all that stuff without path integrals. Okay. Indeed, if you look at the textbook, the way that they derive QED Feynman diagrams, there's no path integrals, no Grassmann variables, no nothing. It's just that keeping track of all the minus signs and stuff like that is a complete headache. Okay, and so this is just a kind of efficient machinery for keeping track of those signs. Yeah, I mean, at the end of the day, we're going to write down the Feynman rules for quantum electrodynamics, and they're going to be exactly what you would have guessed, given everything you know with scalars, except for one minus sign. So everything I'm doing, but it's a very important minus sign. Okay. And so all of this business is kind of that minus sign. I mean, I'm exaggerating a little bit, but yeah. Okay. Good. Other questions? Yeah, I mean, these Grassmann in some sense, Grassmann integration is completely trivial. Like, as you maybe learned last time, when you exponentiate a Grassmann variable, the Taylor expansion truncates at first order. Did you see that last time? Yeah. Okay. So and when you integrate a Grassmann variable, you either get 0 or 1. Like the integral if theta is a Grassmann variable, the integral d theta of 1 is equal to 0, and the integral d theta of theta is equal to 1. Okay. It's the stupidest possible definition of integration possible. So, I'm only calling this stupid operation integration to make it look exactly like it does for a scalar field. Okay. Good. And mathematically, I suppose one can show that this definition of integration satisfies all of the usual rules. The definition of integration and differentiation satisfies all of the usual rules that we expect for a definition of an integral. I mean, if you're more mathematically minded, there's a different name for Grassmann variables that you could use. You could call them differential forms. Okay? They're one forms. Okay? And the statement that they square to 0 is the statement that you take dx, wedge dx, it's equal to 0. Okay? So, so it's just, so there's a completely, so it's just, so if you like, you could phrase everything completely in that language. But this is not a math class, and so I'm using the slightly more pedestrian language of Grassmann variables. Good. Okay, so the point being that these derivatives are anti-commuting variables. So, for example, when we do things like take, I don't know, so, for example, if you took this variational derivative, so this, so these are all being evaluated at y. Okay. So what would you get? Well, the derivative on eta would act on this guy, but you have to anti-commute it through this psi bar here. So you would actually get a minus psi bar of y instead of psi bar of y. Okay. Whereas d by d eta bar of x of this same quantity, you don't have to commute it, anti-commute it through anything, so you would just get a psi of x. Okay. Okay, so these are the signs that appear. And then correlation functions, time-ordered correlation functions, are found by taking these Grassmannian derivatives with respect to the sources of our partition function. Okay. So remember that this is our partition function, okay, our generating function z. It's a function of eta and eta bar. So if you took an eta and an eta bar derivative, for example, then from this term here, that would bring down a psi and a psi bar. So you would be calculating the time-ordered expectation value of psi bar. Okay. So, for example, the time-ordered expectation value, psi bar of x, psi of y, computed in the vacuum state, is, well, the variational derivative with respect to eta of x with a 1 over I out front because there was an I out front here, and a 1 over I times a variational derivative with respect to eta bar of y times this generating function evaluated with eta and eta bar set equal to 0. And as in the scalar field case, one has to normalize the vacuum state so that the norm of the vacuum state is equal to 0. So if you don't introduce this factor of z, then you're computing an unnormalized correlation function. That 1 over z enforces the fact that this the ground state has 0 norm. So for example, without that 1 over z, well, you wouldn't get that the time-ordered expectation value of 1 is equal to 1. Okay, so you can then go ahead and compute this. So in free quantum field theory, z is just a Gaussian integral. And Gaussian integrals are even easier to compute for Grassmann variables than they are for commuting variables. Did you do this last week? Did you compute the Gaussian integral for a Grassmann variable? Okay. It's very easy. It's even easier. Did you guys do it? Yes or no? I mean, basically, you know, the integral over some Grassmann variable. Yeah, okay. Well, if you did it last week, I'll just tell you the answer. Okay. So if you have, you know, so let's say the integral, if you have n Grassmann variables, let's call them theta, that are organized into some vector, and you want to do a matrix integral, so you want to integrate over n of them, then the Gaussian integral, so if you organize these thetas into a vector, and you have some matrix M, and then you have some source term, okay, maybe let's call it eta. Okay. So this is the general form for a Gaussian integral. Okay. So these thetas are some vector. Then if this were a bosonic integral, then you would get the exponential of 1/2 eta dagger m inverse eta times 1 over the determinant of m. Okay. That 1 over the determinant of m is the fact that the Gaussian integral e to the minus x squared times a is 1 over a. Okay. Here, Grassmann integrals scale in the opposite way as bosonic integrals. Okay. And so you get, in fact, something that goes like the square root of the determinant of m, rather than 1 over the determinant of m. Did you guys do that last time? You did. Okay, good. Okay. As far as we're concerned, though, this determinant out front is actually not very important because that's independent of eta. Okay, so that'll cancel out when you divide out by eta here. Okay. The only thing that's important is the fact that, as in the bosonic case, you just get e to the eta m inverse eta. Okay. So here I've written out the Grassmann integral for a finite number of variables. For an infinite number of variables, for a functional integral, it's the same thing, except now instead of summing over the thetas, you have to integrate dx times dy. So that z of eta bar, is going to be the exponential of I times the integral d4x, d4y, eta bar of x times some function s of x minus y times eta of y, where that function is the inverse of whatever operator appears here. That is to say, it is the inverse of the Dirac operator. Okay. So I d slash plus m of s, so that's the Dirac operator. So this would be an x derivative there, has to be equal to delta of x minus y. Okay. So that's just the functional version of the statement that s is the inverse of the Dirac operator. And we know what the inverse of the Dirac operator is. Well, we just derived it explicitly. Okay. So s is just precisely the Feynman propagator that we derived when we were studying the two-point function just by doing an expansion in raising and lowering operators. Okay. So I really encourage you to compare this to the scalar field case in your mind. So in the scalar field case, you had a z of j of x, which was the exponential of I times the integral d4x, d4y, j of x times the Feynman propagator, j of y. And here we get exactly the same thing, except, well, we have a few extra spinor indices that are going along for the ride, and we have the spinor propagator instead of the Dirac propagator. So, oh, I see that I'm out of time. Maybe one question. How thoroughly did you derive this equation last class? Thoroughly? Thoroughly enough that I don't need to give it to you on a problem set? Okay, I shouldn't have, that was not the correct way for me to ask that question. Thoroughly enough that if I gave it to you on the final, you could do it? Okay, okay.
It was thorough, but it was...
Confusing?
He went quite a bit over time, and so at the end of the lecture, people are...
Okay, so you might not have absorbed it in its full glory. Okay, I may put some Grassmann fun on the problem set. Good. Okay, I will stop here and see you on Thursday. Thank you.